Good evening. Tonight, we're excited to have with us Will KW4WZ to talk to us about amateur radio in hobby rocketry. So thanks for taking the time to be with us tonight. And now it's over to you, Will.
Very good. Well, thanks very much, Alex, and thanks membership for inviting me. And I'm going to go ahead and share my screen now. And go into presentation mode, and then I'll do a little laser pointer here, so hopefully you'll be able to follow along. So I'll chat a little bit about not just ham radio, but radio in general in model rocketry. Alex wanted me to do a little bit of a background. So professionally, I work for the Space Sciences Laboratory at the University of California, Berkeley. Although I live in Northern Virginia, I live out near Winchester full-time. My wife, Katie6 DSH, teaches at Shenandoah University. And my background is in computer science. The things I do at Space Sciences Lab, the title is aerospace engineer, and I usually get involved pretty early in programs, helping doing the design and setting up ground testing equipment and helping to develop mission operations. And that usually goes through the launch phases and the early on orbit operations as well. So I get to go to some cool launch places. Bill Donikowski and I are in the payload bay of the Space Shuttle Discovery. We were working on the Orpheus SPAS spacecraft before its launch out on the launch pad. If you see the IMAX film, Destiny in Space, that was narrated by Mr. Spock on Star Trek, the German telescope that he talks about is this, and we did the science instrument on that. And then the last two missions I've worked on, New Star and Icon, were launched with Pegasus rockets, which is pretty cool. You can see the Pegasus here. It sits on the belly of an L-1011 jetliner. The satellite is in the nose cone. The L-1011 takes that up to about 40,000 feet, drops the rocket, and then the rocket flies up into orbit and deposits the spacecraft. So I've gotten to run the mission operation systems on board the aircraft while it's on the ground. I'm not allowed to fly in the aircraft. And then I'm currently working on the SphereX mission for Caltech and the Jet Propulsion Lab. That's an astrophysics mission that's going to study the origins of the universe. Tracers you might be a little bit more interested in. It's a two spacecraft constellation that does space weather. So it studies the Earth's magnetic field and the particles that come from our sun and how those interact to affect things like radio waves. And then MOAB is a fun little experiment that I'm pretty excited about. It's a softball-sized chemistry lab that is small and light enough that it can be carried out to the outer planets in the solar system. And the intent is that it will get flown through the ice volcano plumes of some of the moons of Jupiter and Saturn, and we'll look at the salt water from the under the ice oceans on those moons to look for signs of life. So that's pretty exciting. And I've really been interested in aerospace in my entire life. I grew up in the 60s. I expect some of you were also youngsters during that time and were immersed in the Gemini and Apollo space programs. And model rocketry was a new and vibrant hobby at that point that I was fascinated about. I didn't really know much about amateur radio at that point. I got involved with amateur radio in the 1980s when I was a volunteer on a sheriff's department mountain search and rescue team. And we used amateur radio to augment the sheriff department radios. But my interest in aerospace, where I was working at Space Sciences Lab physically in California at that point, led me to get involved with what it then was SAREX, the Shuttle Amateur Radio Experiment, which had the first human-tended radios on orbit. That turned into SAREX, the Space Amateur Radio Experiment, when we started doing operations on the Russian space station Mir as a precursor to the International Space Station. And then that effort still continues as a more formally international thing these days with ARIS, amateur radio on the International Space Station. And I do IT stuff for that on computers and email lists. And then my wife and I help run the slow scan television gallery for ARIS. Okay, hobby rocketry really got its start in 1957. There was, as I mentioned, a lot of interest in the space program, and there were a lot of youth out there who were trying to build their own rockets. There was not a safe source for commercial rocket motors, so they were building their own rocket motors in the basement, and there were some pretty horrific accidents. So in the 1957 timeframe, a person named Orville Carville started a business to manufacture safe model rocket motors that could be used by young people to fly their rockets. Now, legally, model rockets are different from fireworks. There's an organization called the NFPA, the National Fire Protection Association. It's a nonprofit that develops safety codes essentially for use in industry. Those safety codes then get incorporated into something called the International Fire Code. And then I believe all the states except for California, which has some of their own fire codes, incorporate the International Fire Code into their state laws. So in Virginia, I know that the 3 NFPA codes that deal with rocketry are state law. And then there's a different NFPA code which deals with fireworks. Now, I mentioned 3 codes. There's one code that deals with manufacturing standards, and that's for people who are manufacturing motors for commercial resale to consumers. And then there's a code for low power rocketry and a code for high power rocketry. And we'll talk about that a little bit later. The FAA has separate rules, the Federal Aviation Administration, that controls all things that use the nation's airspace. Those rules are essentially divided into low and high power rockets with some slightly, there's a little bit of disjoint there, so it's not exactly the same. So currently the smallest consumer motor you can get are these things called Micromax. They're about 1/4 inch in diameter and 1 inch long. I just love these. They'll fly these little flying saucer rockets up to 40 or 50 feet. So they're a fun thing to do when you have a small field and you don't want to walk very far. I'll talk a little bit more about this rocket later. This is about 18 inches long and about 2 inches in diameter and can carry payloads. That's sort of a common model rocket sized vehicle. And then here are a couple of high power models. This one is 4 inches in diameter, and you can see that I was barely able to get it standing up in the room. And then this is a 10-inch diameter rocket. Weighs about 40 or 50 pounds, goes up to about a mile in altitude, or it did. So one of the reasons for the stringent safety codes is that sometimes rockets don't work. And so the safety codes are very strict, and we're very careful about following those rules to make sure that you're far enough away from models that when the sad thing happens and there's a failure, there aren't going to be any injuries. If you've been involved in model rocketry when you were a youth, you probably used the Estes black powder motors that are about 3/4 of an inch in diameter and about 3 inches long. Over the years, starting in probably the 1990s, we started getting into larger motors. These are ammonium perchlorate composite propellants, kind of a mouthful. So people usually call that APCP. Black powder motors are very difficult to scale up and have them be reliable. The APCP stuff is easy to scale up. And that's basically the same propellant that's used in things like the strap-on motors for the space shuttles, or for the SLS launch system that NASA has just flown the first instance of to take us back to the moon. Military rockets typically use an APCP-based thing because it's very robust. It's insensitive to environmental, heat and cold, things like that. And then for hobby rocketry, there's actually an interesting combination. It's called a hybrid motor, where it uses nitrous oxide liquid as an oxidizer, and then it uses either a plastic or a wax fuel grain. These aren't all that common. I've flown these a few times, but I thought it worth mentioning because this is all stuff from late in last century and stuff that's really sort of more this century. You would have done black powder if you were flying as a youngster. So here's some examples on the left here. When I was growing up, this size motor, this 3/4 inch by about 3-inch motor was basically what we had to fly with. I remember being very excited when the D-sized motor came in, the Mighty D it was called. But these are all single-use motors. So you buy these and you fly a rocket with them once. These have a paper casing, and then there's a nozzle in here that's made out of compressed clay. So if there is a failure with this motor, there's no high energy metal that gets, flown around the launch field that could cause injury. This is a single-use composite motor. This is basically a plastic casing. So once again, they're designed to split open on a seam safely. And so they'll fail and release the pressure like that. It'll probably destroy your model, but it won't produce shrapnel that's likely to cause injury. These are reloadable motors. So as the motors get bigger, it gets more expensive to do these disposable systems. And so the idea in these is that there's a ductile, there's a bendable aluminum casing that you can clean and reload propellant into so that you can use these over and over again. And they've been engineered so that if there is a failure, that they will fail safely and not cause any damage outside of the safety radius. Here's a picture of a typical propellant kit that would go into one of those reloadable casings. There's a forward closure, which is got screw threads in it. It screws into this pressure casing. There's an aft end, which holds the nozzle. And then there are various O-rings to seal the joints. And these are the fuel grains themselves. And then there's an electric starter so that you can, at a precise time, start these motors up from a safe distance. One of the cool things that we've been doing is lots of competitions and STEM activities involving youth and adults, frankly. 20 years ago, the American Rocketry Challenge started. This is a nationwide competition. There are about 700 to 800 teams each year of 3 to 10 students in each team. They get together to design and fly a rocket to meet a very specific challenge. And it typically involves flying a fresh hen's egg. You aren't allowed to boil it. It's got to be fresh so that there's a fragile payload. And then there's a little altimeter, an electronic altimeter that gets carried on board. And the challenge is with a particular size of rocket to design it so it goes to a particular altitude and has an exact flight duration. This year it's 850 feet, and the flight from first motion to landing needs to be as close to 45 seconds as possible. So this is sponsored by the National Association of Rocketry, which is the 8,000 member hobby organization that is responsible for model rocketry in the USA. And then the commercial sponsor is the AIA, the Aerospace Industries Association, which is a business group that coordinates activities by large aerospace companies like Boeing, Northrop Grumman, Lockheed. So they all contribute and help to run this American Rocketry Challenge. And there are finals that get held in at Great Meadow, which is here in Northern Virginia in the middle of May. If you folks are interested, you can come out and see those finals. The top 100 teams get invited out. They do a fly off. The number one team gets a free, all expense paid trip to either the Paris Air Show in France or the Farnborough Air Show in England. Those air shows get run every other year so that they don't compete with each other. So the number one team goes there. The top 10 teams share $100,000 in cash prizes. And then the top 20 teams get invited to a NASA program, which is, so the TARC effort is middle school and high school. And then the NASA SLI program is more of a sounding rocket program. The goal is to fly payloads up to 5,000 feet. So you're using substantially larger motors and larger payloads, and the payloads are more ambitious. So the top 20 TARC teams get invited, and then universities from around the country can send in their own applications to compete in the SLI. So SLI is interesting in that all the ground crew are amateur radio operators. All the range operations is done using ham radios. And the engineering challenge this year has the teams flying a camera that needs to be controlled by APRS transmissions. So the idea is it has to go to that precise altitude, and then it has to land and deploy a camera. And then commands have to be issued over APRS and the ham bands to make that camera pan and tilt and take images. So that's pretty cool. That's all down at Marshall Space Flight Center in near Huntsville, Alabama. Okay, so what sort of things do people use radios for? The traditional one that started pretty early was remote control. Most remote control of rocket-propelled aircraft and hobby aircraft in general has moved over to the 2.4 gigahertz spread spectrum, either direct sequence or frequency hopping. But there is still some use of narrowband FM stuff in 27, 53, 72, and 75 megahertz. And there's still a 50 megahertz ham band for doing control of remote control aircraft. So that's kind of interesting. The picture on the right is Frank Burke and his daughter. Frank runs a company called Dinosaur Rocketry that does radio-controlled rocket gliders. And you can see the scale model of the Dinosaur rocket, which was a Air Force proposed space fighter, basically from the 1960s that never flew in real life. But Frank has done a faithful model of the Titan launcher that was proposed to do suborbital flights on the Dinosaur. That thing goes up, and then the Dinosaur rocket glider on the top gets deployed, and then Frank controls it down via radio control. Pretty exciting. If you go to his website, dinosaurrocketry.com, he's got a half dozen models that he's selling at this point that are all rocket propelled. So the other big use, although frankly not as big as tracking, is telemetry systems. And mostly that's science data that the hobbyists are doing to report air temperature and air pressure as the rocket ascends, but mostly as it descends under parachutes. And then probably the biggest use is for tracking rockets that might, often we fly these rockets in farmers' fields, and they may, if there's some uncut corn, I'm giving a talk at the national conference in a couple weeks called Lost in the Corn, because that's a frequent lament that you will read on the internet of somebody who had their rocket drift down into the unharvested cornfield, and then it isn't discovered until the farmer, cuts the corn and is harvesting the corn. So I'm giving a talk on direction finding, and telemetry-based tracking systems, which mostly use GPS, the Global Positioning System. So what frequency bands are people using in hobby rocketry these days? Well, the 2-meter ham band is pretty popular for coordination of range operations, as I mentioned, for the SLI stuff. The APRS 144.39 frequency isn't used all that much, although there are, and I'll talk about these in a little bit, there is a commercial offering for rocketry stuff that uses the 2-meter APRS frequency. There's a wildlife tracking band that's used for animal conservation stuff. It's also used by people in the hawk hunting hobby, where you will train hawks and eagles and things as hunting birds, and they will often put a very tiny radio transmitter on there. In the past, those were typically, you would do direction finding with those with a Yagi antenna. These days, there are a couple of systems that they're using for this wildlife tracking that actually has GPS on board. It's amazing the miniaturization of this technology. There's at least one company that's selling a transmitter receiver system in the 222 to 225 ham band. That's a DFing system. So it just chirps, and then they've got a receiving station with a Yagi antenna on it. Most of the GPS telemetry-based tracking systems that you'll see from commercial manufacturers aimed at the rocketry stuff are in the 70 centimeter band. And there's some unlicensed stuff that's being offered at the 443.92, unlicensed watering hole. And then there's some unlicensed 900 megahertz stuff for people who don't have or don't want to get amateur radio licenses. And then there's a fair amount of 2 gigahertz stuff, Wi-Fi stuff, or things that are in that the Wi-Fi allocation that have custom protocols. Now, talk about that a little bit in a couple minutes. So I tend to give this talk to rocketry audiences where I'm trying to sell them on the advantages of getting an amateur radio license. So this is kind of flipped in that I'm spending a little bit more time talking about rocketry technology as opposed to the radio technology. One of the things I talk to about the rocket folks is the proprietary nature of a lot of these non-licensed commercial systems. And there are a lot of systems out there. The disadvantage of a lot of those things is that if you can't get good packets, then you can't decommutate the data, and so you can't get any information from your GPS system as to where your rocket is. And because of the sort of weird nature of these commercial systems, they're very difficult to DF. And the spread spectrum systems are just really difficult to DF unless you have, some very specialized equipment. So to the rocketry crowd, I sell the advantages of the automatic packet reporting system, APRS, that hopefully you folks are familiar with. It's got a common allocation at 144.39 in the US, which makes it really convenient to use. If you haven't done APRS from space, 145.825 is really popular. There's a continuously, except for spacewalks and some docking activities, APRS system on board the International Space Station these days. And there are a handful of microsatellites that are doing 145.825 APRS stuff. So there's actually a lot of resources available in orbit for doing this stuff. And then if you want to do terrestrial stuff, just pop over to 144.39. and there's an example map on the right of the Winchester area and some of the weather stations and ham radio operators driving around near my area being reported by the APRS.FI Foxtrot India site, where there are data nodes that will capture that APRS traffic, report it to servers on the internet, and then you can have these maps and follow people around and do coordinated activities. Sadly, there's not really that I'm aware of, a fixed 70 centimeter watering hole frequency. And so, ham radio is secondary on 70 centimeters, of course, but so people, just end up picking quiet frequencies in their own area for rocketry-based use of APRS in 70 centimeters. So Alex thought it might be worth my going over a little bit of GPS background. I usually do a lot of this for the rocketry crowd because they aren't familiar with it. Please bear with me if you're super familiar with this. So global positioning system, it's satellite based. This nice little graphic here is showing in red that from your position on the Earth, you can usually see a handful of satellites, and your receiver does some math by knowing where those satellites are and their position relative to you. It can calculate your position on the surface of the Earth to within usually a couple of meters for a civilian receiver. If you play some games, we can talk about that later. If you're curious, you can get down to centimeters. The cool thing about this is it's pretty much global. Precision isn't as good at the poles as it is down at lower latitudes, but it is basically a worldwide thing, and it can be used in space. So lots of low Earth orbit and high Earth orbit satellites are using GPS-based systems now, both to get the time, but also to get their position and velocity stuff. And it's a game changer for doing science in low Earth orbit. The military had a requirement that the assets on the ground be receive only because they didn't want the troops on the ground to be having to transmit. There's a difference between military systems which use multiple frequencies to help compensate for some of the variations in the ionosphere that will affect the accuracy. And the civilian subsets typically have less. If you're curious, we can get into some details about clever things that the civilian community has done to increase their accuracy, in spite of the military attempting to inhibit that. And the GPS system is a U.S. military system, essentially. And so internationally, people have not wanted to depend upon the U.S. military for their military or civilian stuff. And so GLONASS is the Russian system. These are all basically interoperable systems, although they have different space assets. Galileo is a system put together by the Europeans. Baidu is the system that the Chinese have put together. All to do this, locate you on the surface of the Earth and get you accurate time. A little bit of stuff. Geostationary orbit is where a satellite is fixed in relationship to you. So your Viasat, your television antenna satellites that you see on so many roofs these days, they're pointing at a fixed location. That's the advantage of the geostationary Earth orbit. GPS satellites are in a medium orbit, so they're in about a 10 or 12 hour orbit. So they actually move. That's what you were seeing in that graphic beforehand. But GPS was really intended to do precision targeting of primarily intercontinental ballistic missiles. We had fairly accurate launch vehicles, but you needed to know very precisely where you were. And for mobile platforms like submarines or aircraft, where you needed to be mobile in order to survive, so that your opponent couldn't kill you before you could launch. It was difficult to know before GPS precisely where you were. So GPS was intended to replace celestial navigation, where you looked at the stars, early radio and early satellite navigation systems. And the first launch was 1978. New satellites are still being launched. There's a contract was just let to get a replacement vehicle put up on orbit. And I put in Dr. Gladys West, who's a Virginia resident. She worked for the Navy in the 1950s. Her Wikipedia entry makes fascinating reading, but she basically developed much of the math that was needed to implement the GPS system. So she's still around. She's getting pretty old at this point. I encourage you to take a look at her Wikipedia page for somebody who is making some amazing contributions to the field, starting in the 60s and continuing for many decades. So GPS limitations. I want to put this chart up because I thought it was really interesting. GPS is pretty good. This 9 meters is a little bit old. Civilian systems will typically these days get you down to 3 or 4 meters of position accuracy. One of the disadvantages of GPS is that it can be jammed or it can be spoofed. So it's possible to broadcast fake signals, and civilian receivers will pick those up and may think that they're in a different location. This has been such an issue in the fighting in the Ukraine that I know that the Russians have been talking about going back and using LORAN, which is an HF radio broadcast. This is a technology that's been around for since the last quarter of last century. But they're talking about using that as a fallback because GPS has been denied to them in the Ukraine area. And then there's some other things. So you can see clearly that if you want to get an intercontinental ballistic missile on somebody else's silo within 50 or 100 feet, which is what you'd need to do to break open that silo and destroy the missile before it get launched at you, you can't really use any of these systems. You really need to know your location precisely enough to the few meter range so that you can then launch your missiles and have them impact. GPS is also used for targeting bombs these days. So there are lots of airdropped weapon systems from human-tended aircraft and UAVs at this point that all use precision GPS navigation to try and hit a precise target and avoid collateral damage. But there are some problems with GPS. Selective availability was something that the military had used to deny precision availability of GPS signals. It's been turned off. That's probably not really relevant. You can read about that on the web if you're curious. The ionospheric variation, though, day to day during heating, and you're familiar with this from your HF radio propagation and stuff, but also solar activity will affect the ionosphere, and that affects the speed at which signals propagate through the atmosphere from outer space where the satellites are transmitting to the receivers on the ground. And knowing the precise time difference from when a satellite transmitted a beep and when you receive it on the ground is key to getting a precise location on the ground. So understanding ionospheric behavior is key. And so that's why satellites like the Tracers mission that I'm helping with one of the instruments that's going to be on that mission that we're doing at UC Berkeley is so important, so that we can predict space weather so that people can understand impacts on not only military operations, but also things like civilian operations or rescue missions. If you know that your medevac helicopter is going to have compromised GPS, you may decide to do some different option if you know that space weather is going to be bad. One other thing that's not completely obvious just at first glance is geometry of the GPS constellation. So if your receiver is listening to 3 or 4 satellites that are very close to each other, they will not produce as precise a position solution as if it's listening to 3 or 4 satellites that are spread out at a wider angle. And we can talk about that later if you're curious. And there's lots of stuff on the web about that. Probably the biggest thing for hobby use is signal blockage, in that GPS systems aren't happy if the antenna is behind metal or some carbon composites that are block radio signals. And for your navigation in the city, for example, if you get the GPS signals bouncing around off of building surfaces, you can get some compromised accuracy in your GPS solution. The other big limitation for GPS using and tracking hobby rocketry and aircraft and basically anything that's moving is you need telemetry to get that data back from the rocket or your aircraft or your high altitude balloon to the ground. And so if you can't get a good solid data link to get those packets back, then you aren't going to be able to decommutate them, break the data apart, and find out where your vehicle is. There are also restrictions in the civilian GPS receivers in terms of altitude and speed lockouts to prevent people from taking a civilian receiver and using it in a weapon system. And so typically, and these vary by manufacturer, so you never know until you try from a particular manufacturer what's going to happen if you get up above 18 kilometers or if you get up above about 500 meters per second, what it's going to do. Some of them stop working. Some of them start producing degraded solutions. Some of them produce a much lower frequency of solutions. Some of them will work if you're at low speed, but you're at high altitude, like on a high altitude amateur radio balloon. You can get some where the firmware will continue working because the balloon is at a low velocity. In terms of rocketry, there's a thing called jerk, which is the change in acceleration of the GPS system can cause it to lose lock on the satellites. And so in hobby rocketry, it's not uncommon for you to have a good GPS solution when you're sitting on the launch pad, and then you lose it during boost when you're accelerating rapidly. And then the receiver will reacquire a signal from the GPS constellation when it gets up near the apogee of its flight, and then it will maintain one through the relatively low speed and constant parachute descent to recovery or to landing. Okay. So there are a few different categories of products that are currently available, and there's lots of consumer stuff out there that's intended for tracking cars, asset management, stuff like that. Those things typically use cellular transmitters, cellular phone transmitters to get the GPS telemetry back to you. For rocketry applications, that's often an issue because we tend to fly out in remote areas where there may not be good cell phone coverage. And so I tend to try and discourage the hobby community from considering those solutions, even though they're relatively inexpensive. And you do have to typically buy a data contract that's usually, tens of dollars per month for those, but they may not give you good coverage out where your rocketry launch field is. There's an emerging field of tracking products for unmanned aerial systems, so drones, both fixed wing ones and the more familiar multi-copters. And then there are a handful, there are about a half a dozen rocketry specific systems. And I'll talk about a couple of those here, and then I'll point you to a web page that I put together that talks about some of the advantages and disadvantages of the commercial offerings, and I try and keep that available. These are two of the products from a company called Big Red Bee. This is a 70 centimeter GPS. This is an APRS system. You can program the rate at which this thing transmits APRS packets. It's 70 centimeters, so you need a dedicated receiver on the ground. Fortunately, there are a couple of nice ham radio handhelds that have a TNC built in that'll decommutate this stuff, and then will point you right to these transmitters. So the Kenwood THD-74 is gone end of life. Hopefully, when they get some of their parts situations straightened out again, they'll come back with a new APRS model, but you can still find those on the used market. The THD-72 is nice, also available on the used market. Yaesu has got their FT5D series, which is a 2 meter, 70 centimeter handheld that's got built-in APRS capability. Very nice radio, very small, easy to transport. So those will all receive packets from this thing, and will tell you exactly how to go and find your rocket. The smaller transmitter is a 70 centimeter DFing transmitter. So this just sends out a beep and then a Morse code call with your call sign periodically, and you use a Yagi antenna to fox hunt and find this thing. Greg, who runs Big Red Bee, has a 2 meter APRS version of this thing, and he sells these for use in high altitude balloons as well as rocketry. And he's had some of these things modified for use in CubeSats on orbit. So it's a pretty sophisticated system, but it's a little bit large for these days. There's a company called Altus Metrum that makes this GPS. You can see the GPS antenna here, and the backside has got the 70 centimeter transmitter stuff. The battery to run it is almost larger than the transmitter itself. It's pretty amazing technology. The Altus Metrum series of products, this will transmit 70 centimeter APRS packets, and it's also got a proprietary. Well, it's open source, so it's published, so it meets the ham radio requirement of anybody being able to decode the packets if you want to receive it. So this thing is dual use. You can do just plain APRS on it, and then you can have alternating packets if you want that will transmit other telemetry data. So it's really a very nice system. Very small, as you can see, just a couple inches inside, weighs hardly anything, just an amazing product. So this is a rocket from Estes Industries. Estes is still around. They were the company that basically got started in the late 1950s to sell the model rocket motors to try and reduce the accident rate amongst the youth who wanted to be involved in the space program, but didn't have the expertise to safely mix their own motors. So Estes is still around. And this is a rocket of theirs called the Green Eggs, from this horrifically green payload compartment here that's about the same size as a hen's egg. So the intent for this rocket is to allow people to fly a hen's egg. There's a parachute for recovery. It uses a 24 millimeter diameter black powder motor, mostly a D-sized motor, which is fairly powerful, and will get this rocket up to 800 or 1,000 feet if you don't have any payload on board. I've been using it to fly. You know, it's really interesting. We're living in sort of a golden age of maker stuff with 3D printers and CNC and all these electronic companies like Adafruit and SparkFun, where you can buy an Arduino computer here for about $20. It's got an RF system in it, a 2.4 gigahertz system that'll either do Wi-Fi or it'll do their own custom protocol called ESP Now. On the back side of this board is temperature, humidity, and barometric pressure sensors, so you can get detailed atmospheric readings. This up here is a little tiny GPS receiver, and then there's a display. So I programmed this Arduino computer to get temperature, pressure, humidity, GPS information, so time, location, altitude, and then it telemeters it to the ground to another one of these Arduino computers, which knows where it is because it's got a GPS. And then it's got an inertial navigation system on it. So this chip is actually a three-axis compass system and accelerometers and angular rate sensors. So this thing can calculate all by itself where this is and what direction it's pointing. And so between the telemetry that comes down over the 2.4 gigahertz link to this, and this information about where the system is on the surface of the Earth from GPS and where this thing is pointing, I wrote some code that tells you, are you pointing left or right to go and pick up your payload. Just amazing stuff. Last year, I did a presentation at the national conference at NARCon, which is the week after next. I think I mentioned it, for the National Association of Rocketry conference. And I was trying to encourage people to do a no solder data package that they could fly. So you don't have to solder any wires for this. You just use these little data cables to daisy chain these systems together. And then with a little bit of software, you can fly this altimeter. And then for this year, for the conference, I'm presenting, you know, the addition of this ground station so that you can do tracking stuff. So if you're interested, the conference is next weekend. I can point you to that. All the presentations will be up on YouTube in about a month if you don't want to pay to go to the conference. And that is, you folks have been very patient. Nobody's thrown anything at me that has gotten this far. I was gonna mention in the references, you can go to a web page. It's my call sign, Kilo Whiskey 4 whiskeyzelo.com. If you go to NARCon, it's got my presentations from the last few years about various subjects, including rocketry and amateur radio. I wanted to mention that there's a very active model rocket club in Maryland called NARHAMS. Once a month, they do a public model rocket launch at the Goddard Space Flight Center Visitors Center, and you can go to that. And they have a lot of youth who show up at that and will do their first rocket launches. And then they also do another launch every month at a much larger field where you can fly larger rockets. At the visitor center, it's pretty small rockets because it's a small area. And then feel free to send me questions if you think of questions later. And I am going to unshare my screen if I can. And put you back to Alex, I think.
Well, thanks, Will. That was fabulous. What an interesting run through rocketry and amateur radio and GPS. Wonderful stuff. So do we have questions for Will? I see Mark Mark, up, over to you.
Yes, I noticed in one of your slides, there was something that looked like a license. It said was a card or something that had your name on it and various other pieces of information. Is that like a license to launch these things, or what is that exactly?
Yeah, great question, Mark. Thanks. So that's a flight card, and it's common at organized launches where I fly with NOVAR, the Northern Virginia Association of Rocketry, out at Great Meadows. It's not uncommon for us to have 100 Cub Scouts show up, literally 100 Cub Scouts show up to fly their rockets. And so what we do is every time a rocket flies, you fill in a flight card that that has the name of the rocket, who the flyer is, what size motor it is. On the back of that, you didn't see that there's a little safety checklist. And then the protocol is that you take that card and your prepared rocket up to a safety inspector who does a brief safety inspection, and then you get assigned a launch pad and you'll fly your rocket. For low power rockets, a license is not required. For rockets that are larger, these high power rockets, there are in the US, there are 3 different levels of licensure in order to buy and fly those motors. And so each letter of motor size is double in power. And in the US, the largest commercial motor you're allowed to fly is an O. The rockets that you typically see the Cub Scouts fly are A's, and so you can count the letters and do the factor of 2 stuff. O motors are usually 4 inches in diameter, and they'll be 2 to 3 feet long, and they'll cost $500 to $1,000 for the propellant per flight for those things. So I don't fly. I've flown some M and N motors, which are about $500 a flight. I don't do that often. But that red rocket that I showed earlier that was blowing up, that was on an M motor that immolated. So that was a $500 for the motor. And then the manufacturer replaced the propellant and the casing because it was a manufacturing defect. But the $1,000 rocket that immolated all the electronics. So there was an APRS transmitter, there was a DFing transmitter, some altimeters that I didn't show you the movie because it's still heart-wrenching to watch that thing. Okay, so sorry, that was a long story. That's the deal with that card. So that was the flight card for that particular flight. That was the altimeter rocket. So I tend to take a picture of the flight card and the motor so that I then have a record that I can correlate with the recorded telemetry from the flight, so I can go back and remember what I was doing. Thanks. Good question, Mark.
Thank you.
There was one other question. No? Okay. Well, thanks. I really appreciate the chance to come and talk to you folks about, I'm passionate about rockets and I'm passionate about amateur radio. Feel free to come out and fly with us at NOVAR. If you have kids or grandkids, it's a great excuse for you to come out and fly some stuff yourself in the guise of doing it for the grandkids. And contact me or contact the NARHAMS folks. They love to have new folks show up. And the NASA Goddard Visitor Center is a great venue for kids to fly small rockets because you're flying a rocket at a NASA center. What can be cooler than that?
Great, wonderful. Well, thank you for taking the time to be with us and for sharing all your great knowledge and experience. We really appreciate it. Thank you, Will.
Thank you. Appreciate your patience.